Assessing the team's history and setting goals for the future, we thought of 2 missions to be embarked on Osiris. Pegasus is the first satellite built by the team, a 4-unit pocket cube with a PEG structure. The onboard missions will be a duel between 2 radios already used by the team, LoRa and NRF24 LO1, to check transmission rate, package integrity, and distance reached. The second mission is a camera test to see if we can, in our next rockets, board an integrated system in the structure that transmits the entire launch, just like in the last cooperation.
We developed a D-class solid rocket motor that delivers 86 Newton-seconds of impulse. The rocket mass is 1.6 kg. The motor uses KNSB propellant with a mass of 740 grams, featuring a Bader grains geometry with 3 segments. The motor also uses snap rings as fasteners and O-rings for the sealing system. The internal ballistic parameters and the thrust curve are shown below. In order to check if the fuselage temperature was acceptable, the propulsion team developed a thermal analysis that is shown below. Structural simulation softwares were used in order to validate the analytical calculations. The motor structure was designed to tolerate a pressure that's twice the operating pressure. We developed a CFD nozzle analysis for check the performance and also guarantee a better efficiency of the nozzle.
The rocket will be divided into 4 main sections, being payload bay, recovery section, avionics section, and motor section. The payload and avionics fuselage will be made of fiberglass, while the recovery section and motor section will be made of carbon fiber. The sections will be united by 3 6061T6 aluminum alloy couplers. Static structural simulations were made to make sure the couplers could withstand the maximum loads experienced in flight. The loads on the eye-bolts at parachute deploy were also simulated.
Now for the aerodynamics system overview. The rocket will use an elliptical nose cone, inside of which is located a payload. 4 elliptical airfoil fins will guarantee the passive stability in flight. The following tables presents the main flight events. Launch rail departure stability is 1.52 calibers with a 2 meter per second crosswind component. Maximum stability margin is achieved in flight, which is 2.64 calibers. Flight profile was then simulated using OpenRocket. The apogee for a 87-degree launch angle is 1,093 meters. The center of gravity was obtained using SolidWorks and is located at 73.12 centimeters from the nose cone. The center of pressure was obtained using ANSYS Fluent and then compared with OpenRocket values, yielding acceptable results.
The avionics bay was designed to assure immediate access to all the components, its reuse and efficient organization of cables, and space and mass optimization. To get the safe condition, the system had to remove before flight with a Hall effect switch and a pull pin switch. This is the redundant trigger system with the pylon multi light. The avionics subsystem is able to trigger 2 parachutes. The first will be based on the data of high vertical velocity and the velocity vector orientation. In case of success of the first, the second trigger will take place because of the high measurements and time of the first activation.
The recovery subsystem will use 2 parachutes to slow down the rocket, which will be ejected at different moments during flight. A hemispherical drogue parachute and a tricone main parachute. Tied with shock cord to eye bolts attached to each of the couplers. At the apogee, a servo motor will be activated, unlocking a lateral hatch, ejecting the drogue parachute to stabilize the rocket, and at an altitude of 500 meters above ground level, a tether system will be undone and releasing the main parachute from the recovery compartment.
The total mass of the rocket is around 44.9 kilograms. The total estimated cost for this project was around R$3,264.66. Thank you very much.